Here we've got the notes for section 9.4 to the series. So series are similar to sequences, except you are adding the list of numbers together instead of just having a list of numbers. So here we've got something about summation notation. All right, so in summation notation, the sum of the terms of the sequence, A1, A2, A3, so there's your sequence, is denoted, that's the Greek letter sigma, k equals 1 to n of ak, which is the sum of a of k from k equals 1 to n. The variable k is called the index of summation, so first term, second term, third term. So you don't necessarily have to start at 1. You go up to the nth term. So you want to do the first 10 terms, it'd be k equals 1 up to k equals 10. Okay, so sum of arithmetic and geometric sequences. So let a1, a2 up to an be a finite arithmetic sequence with common difference d. Then the sum of the terms of the sequence is given by this, a1 blah, blah, blah. And then here is our formula. There are two different versions depending on what you know. This equation uses the first term and the last term in the list. This equation depends only on the first term, which I have no anything else. So if you look at example 1, it says a corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the row preceding it. The top row has 24 seats. How many seats are in the entire section? So we start at 8, we have 10, and then blah, 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 all the way up to 24. So we want to know how many seats total are in that section. So I can actually use either of these two equations because I know the first and last term, 8 and 24. Actually, I need to figure out how many. I need to figure out how many rows there are. I need to figure out my n. So anyway, so let's see here. We would do 24 minus 8. So this is figuring out n. That is 16 divided by 2, the common difference. So there are and then we have to add 1 extra 1 because you have to, this is the number of steps I took, which means there are 9 numbers in my list total. You could actually work it out: 8, 2, 12, 14, 16, 18, 20, 22, 24. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this over here, you do first minus last. So there's a difference of 16 divided by 2. It's 8 steps, which means there's 8 spaces in here, which means there's 1 more. There's 9 numbers, so n is 9. So let's use this formula. So 9 times the first term plus the last term divided by 2. So that is going to be, calculator on, there we go. So 8 plus 24 divided by 2 times 9. So there are 144 seats in that section. Or I could use the other formula. So 9 over 2, quantity 2 times 8, plus 9 minus 1 times the common difference. So that formula. So that's, well, let's just type that in exactly as is. 9 halves times 2 times 8 minus 9 minus 1 times 2. Oh, it doesn't like that 2 at the end. I'll have to put a times there. Whoops. Oh, that's because it's plus. Plus. There you go. Also 144. So either equation works, depending on just... So if you have a very long list, it may not be feasible to find the last number in your list. So that's why you have this version here that does not depend on the value of the last number. Okay, so you got sum of a finite geometric sequence. Remember, geometric sequences are multiples. So A1, A2, and N are multiples of each other. So there's only one version here. So A1's your first term, and R is your multiplier, N is the number. So find the sum of the geometric sequence for -4/3. So to find the value for R, you take any term and divide it by the previous term. So -4/3 times 1/4. So the R value is -1/3. So let's see here. First term, second term, third term, fourth term. So we got 10 terms total. All right. Oh, actually, we have 11 terms because remember the exponent is in the generic form. This is A1 times R to the n minus 1. So if n minus 1 is 10, the n value is 11. And you could, once again, work it out until you got to this. That's to the 0th, 1st, 2nd, 3rd, which means if I start counting at 0, that's the 11th number in the list. So my formula is going to be A1, 4, times 1 minus, so R is negative 1/3 to the 11th, all over 1 minus negative 1/3. Okay, so let's work this out. So negative 1/3 to the 11th, 1 minus that number times 4. Divided by 1 minus negative 1/3. Doop. So we get this really ridiculous decimal, 177,148 over 59049, which is about 3. So it's pretty close to 3. Okay. So infinite series. So an infinite series has infinity here, so this list goes on forever. So sometimes referred to the partial sums, which is you add up a certain number of them. So all of which are true sums, approaches a finite limit s. In this case, we see this series converges, so the values, the sums level off. If the limit of the partial sums does not exist, then the series diverges or has no sum, and has no sum. Okay, so example 3, for each of the following series, find the first 5 terms of the sequence of partial sums. Which of the series appears to converge? So we need to find S1, S2, S3, S4, S5, so on and so forth. So S1 is just actually the first number, so 0.1. S2 is the sum of the first 2, so 0.11. S3 is the first 3, 0.111, so S4, 0.1234, and S5 would be, 5. So what this is if we keep going, so Sn, if you notice the pattern, is 0.1 repeating, which is 1/9. And since it has a value, it converges. So here, so S1 is 10, S2 is 30, S3 would be 60, S4 we add 40 and get, 100, and S5 we would add 50, the next term in the list, which would be 150. So if you notice, these numbers keep growing. They're getting larger and larger and larger. So that means this diverges, because these numbers are not leveling off, they're getting bigger faster. Okay, so let's see here for this one. So S1 is 1, S2 is 0, S3 is 1, S4 is 0, S5 is 1. This also diverges because they do not level off to a single value. It bounces back and forth between 1 and negative 1. So S of n does not exist. All right, convergence of a geometric series. So the geometric series from k1 to infinity of a times r to the k minus 1 converges if and only if the absolute value of r is less than 1. If it does converge, the sum is a divided by 1 minus r. So for this problem, determine whether the series converges. If it converges, give the sum. All right, so for this one, our r value is 0.75. So the absolute value of r is equal to the absolute value of 0.75, which is 0.75, which is less than 1. So it will converge. And then to find the value, we take a, which is that number there. So 3 over 1 minus 0.75, which comes out to be, that's 1 minus 3/4 is 1/4, 3 divided by 1/4 is 3 times 4, or 12. So this series, if I let k get very large, the numbers will eventually add up to 12. So for this guy, let's see here, r is negative 4/5. So the absolute value of r is equal to the absolute value of negative 4/5, which is positive 4/5, which is less than 1. So this one will also converge. In this case, the first term is 1. So 1 over 1 minus r, so negative 4/5. So 1 minus, that's 1 plus 4/5, so that's 5/5. That's 9/5 on the bottom. 1 divided by 9/5 is 5/9. Alrighty, so for this one, r is equal to pi over 2, so the absolute value of r is equal to the absolute value of pi over 2, which is just pi over 2. But pi over 2 is greater than 1, so this diverges. And down here, what are we multiplying? So remember, we're looking for the r value. So even though this is written as a sum, it's a times r to the n minus or k minus 1. So r is what's multiplied here. So I'm doing this formula. So to find r and divide any term by the one in front of it. So r is 1/2. So the absolute value of 1/2 is 1/2, which is less than 1. So this will converge. It will converge to 1 over 1 minus 1/2, or 2. Okay, last one. Example 5. Express the repeating 2.34 in fraction form. All right, so let's see here. So this is the same thing as 0.234 plus 0.123234 plus 0.123456234 plus 0.123456789 so on and so forth. So this is actually a geometric series. Each of these is multiplied by something. These zeros shift the same amount each time. So we need to find our r value. So you divide any term by the term in front of it. So 0.00234, whoops, not enough, 0.123234 divided by 0.234. So that is 0.001. Yep, so there's r, which is less than 1. So in fraction form, let's see here. So a over 1 minus r. So a is 0.234 divided by 1 minus 0.001. So 0.234 divided by 0.999. Oh, and I can multiply both by 100, or 1,000, sorry, to get rid of the decimal points. So we got that. And let's see if this reduces. So 239 over 999 is, 234, I got sloppy. 234 over 999. This is 26 over 111. So that's what that repeating decimal is. And that's actually how you find the fraction for any repeating decimal. But that brings us to the end of the section.